So the scoop is as follows. I'll have linear transformations, then we have inner product spaces, diagonalization, canonical forms, then lastly bilinear and quadratic forms. Linear, quadratic, and the Hermitian forms. So that is the scoop, but normally there is something here which is supposed to start. That is vector spaces. But vector spaces are usually taught in linear algebra 1. So I assume that you have prior knowledge on vector spaces. Maybe you can tell me. And also, I was told that this is an audience of high school teachers. So some things may be obvious. Or you can tell me, but that's the scope. The first section, vector spaces. I want to believe that they were covered. If you haven't been taught vector spaces, then you tell me so that we start from there. But the scope of
Shall
linear
request
algebra 2
you.
is supposed to start with linear transformations. Come again?
We shall request you to revise a little with us because personally I did not understand the vector spaces.
But they were covered.
They were hinted on.
So since they were hinted on, I'm also going to hint on them because vector spaces is not part of the scope of linear algebra 1. It is not part of, but it is just a prerequisite. Yeah, so there are some things which I'm going to comment on, but not all of them. So since you have requested, let me go through the brief.
It's very slow. Oleng order. No, okay, dish. Malo in algebra. Huh?
I'll brief about vector spaces. Mainly in vector spaces, you look at things to do with vector addition and examples of vector spaces. Brief about the mathematics of vectors. So there are some prerequisites. Like which ones? Vector addition, i.e., if u is 2, -5, 2, 5, let me take 2, 5, and v is 7, 9, then u plus v would be 2, 5 plus 7, 9, and this gives 9, 14. Similarly, we have scalar multiplication by a scalar. Scalar multiplication, for example, if I let beta be a scalar, if beta is a scalar, then taking u, beta times u, this will be beta times 2, 5. So this gives 2 beta, 5 beta. Like that. For what? For large number of tuples, we do the same thing. We do the same thing. What do I mean? For example, let u and v be vectors in Rn, the n-dimension space. If I start with R, this is a real line, the usual number line, a real number line, R. That is if n is equal to 1. Then if n is equal to 2, then I'm in the Cartesian plane, like these points U and V. They are taken from the Cartesian plane, XY plane. Then if it is 3, then I am having 3 planes. I'm having the three axes. I have the x-axis, y-axis, and z-axis, like that. So Rn, I'm operating in n-dimension space. So we have tuples from U1 up to UN. What do I mean in particular? For example, if U and V are in Rn, then U should take on elements like A1, A2, up to AN. that. Then V should also take on elements B1, B2 up to Bn, like that. So if I'm in R, the number line, then I'm having one entry. For example, you will be A1 and V will be B1. That is if I'm on R. Then if I'm in R2, there are 2 coordinates for each point. So Rn, I'll have n coordinates. So in this case, it is easy to see that U plus V is so you add corresponding components. This will be A1 plus B1, A2 plus B2,